this video, I'm going to go through 3 problems that were in the PowerPoint class notes under related rates. It was the oil rig, the airplanes approaching the airport, and the coffee dripping through a filter. They're listed in the PowerPoint notes for related rates, but they were not worked out, so I thought it would be good to work them out. So let's start with that oil rig problem. What you will want to do is first read through the problem yourself in those PowerPoint notes. Try to understand it. So you may want to pause the video, take a moment, and do that before we get started. Okay. So for this particular problem, or any time you're doing a related rates problem, you really need to understand what's going on. And you really need to label everything. It is so important to understand the variables that you're going to utilize and label them correctly. So for this one, you've got this oil rig, and then the oil is spreading out circular and increasing. The main question is, of course, how fast is the area of the oil spill increasing? So that's what we're looking for in the problem. So let's understand some of the information we are given in that problem. We are given actually 2 pieces of information about the the radius. And one of the things is they want to know how fast the area is increasing when the radius is at exactly 100 meters. So, I might have said 100 miles. Now I can't remember. I think it was 100 meters. So, that is a moment in time that the radius actually hits 100 meters. So there's a particular speed that the area is increasing when the radius is at 100 meters. Now, if the radius is a different size, that change of rate in the area is going to be different. So we are looking at it when it is at exactly 100 meters. But we're also told that the radius itself is steadily increasing at a rate of 30 meters per hour. Okay. There's a couple things you need to understand when doing these related rates problems. And a lot of this I went through in the intro video. When you are defining something as a rate of change, you're defining it with respect to time. So, for example, this rate of change for the radius needs to be defined as dr dt. Where the radius of 100 is a stationary moment. Well, not really stationary. It is at a particular moment in time when the radius is 100 meters. Okay. And why do we do this? It's really important to get those variables defined properly. Okay? You've got to understand what is a rate of change, the 30, and what is not a rate of change, the 100. And set them up correctly. The other thing is you need to figure out, and this is pretty important, I'm going to put it in red, what are you looking for? What do we want in this problem? We want to know how fast the area is increasing. Well, is it a rate of change we want? Yes, it is. So then we have to write it with respect to time. And it's the rate of change of the area. So it makes sense to write that as dA dt. That's So when we finally get to our equation, the only unknown we should eventually have in order to solve that equation is the dA dt. Okay? So, a couple things. Because dr dt is increasing, the radius is increasing at a rate of 30 meters per hour. That means that our change here is positive, so we keep 30 as a positive. Anytime you are decreasing, you are going to write that rate of change as a negative, but our radius is increasing. And we want to know exactly, when that's 100, what is the rate of change of the area? Okay, so take that time. It'll make the rest of the problem so much easier to define everything. Then, well, this is an obvious equation. It is circular. We're looking at an area. Area of a circle is simply A equals pi r squared. Now, the next thing you want to ask yourself, is there anything in this problem that remains constant? So, area is constantly changing, radius is changing. There are no constants. We will get to a problem where there is a constant. I believe in the, well, maybe not in this group today, in this video, but in the last video we did, in the intro video, remember there was a ladder sliding down a wall? That ladder always remained constant. So if there's ever a constant, you put that in now and simplify your equation before you actually do the differentiation. Now, we need to differentiate this with respect to time. So we're going to use implicit differentiation with respect to time. So if you take the variable a to do the power rule, you're just going to get 1. But because we're doing it with respect to time, not with respect to a, you're going to have 1 times dA dt. Okay? Pi is, that's just, you have pi r squared, so that pi is not a variable. Please don't think of pi as a variable. We're not doing the product rule here. Pi is just a number. It's the coefficient of r. So since pi is your coefficient and r is being squared, using the power rule says we're going to move 2 times pi out front. The radius goes to the first power, but because we are differentiating with respect to t, we write dr times dr dt. Again, if we were differentiating with respect to r, be dr over dr, and we wouldn't have to write that. Okay. Now that you've differentiated, as long as you labeled everything correctly, we should be able to fill everything in, and the only thing we'll have left is that variable that we want, which is dA dt. So we don't know dA dt, that stays dA dt. We have 2 pi 100 meters, and then dr dt, of course, is meters per hour. It's really important, I kind of mentioned this in the intro video, that you put your measurements into the equation and work out your measurements, because ultimately your measurements should match the final answer. So what do we mean by that? Well, let's get our final answer. dA dt, this one's nice and easy because it's already solved for dA dt. We'll just leave pi, that's fine. So 2 pi 100 times 30 is what? 6,000 pi. And then we have m squared over hour. So a couple things about the measurement. We're dealing with an area. We know the measurement of area is always squared, so that's where the meter squared comes in. That's perfect. Per hour, any measurement that is a rate of change is going to have that per some measurement of time. So perfect. And there's our answer. So that first one in PowerPoint's pretty straightforward. Very similar to, I think I did an expanding circle in the training video, in the intro video. All right, let's move on. And the second problem you have, so please take a moment if you haven't already to go through and read the problem about the two airplanes approaching. And what I want you to do is on your own, see if you can at least identify all your variables. And see if you can come up with, you don't need to use the notation they use. I tend to prefer using dA dt versus a prime of t. This would be equivalent to a prime of t. I just think it's a little bit easier to work with. Okay, I think in the notes they start to use the other notation. All right. So we have our airplanes approaching, right? So airplane 1 is approaching, getting closer to the airport. Here's our airport, right? And then plane 2 is going north. We'll call him plane 2, and he's heading north. All right, so when plane 1 is a distance, and we want this. All right, let's finish the diagram first. So I'm going to go and use measurements x, y, and z, but I'm just going to call this distance x. I'm going to call this x, this y, and that z, just to make it easier for us. All right, and if you used other measurements, that's fine, but this way, or if you haven't tried it yet, take these measurements and hit pause now and see if you can come up with everything. All right, so x, if you read the problem, when x is 180 miles, the rate of change for the airplane is 120 miles per hour. So because that would be dx dt, because it's a rate of change. Now here's where you need to be careful. The distance to the airport is decreasing. Since the distance, the rate of change to the airport is a decreasing distance, that is going to be negative 120 miles per hour. All right. For plane 2, when plane 2 is 225 miles, it is traveling at the same time, it is traveling dy dt at negative 150 miles per hour. Again, negative because it is shrinking the distance. As it gets to the airport, that distance is getting smaller. Okay? So there's all the information we're given in the problem. You know, so at a particular moment in time, plane 1 is exactly 180 miles from the airport, and it is traveling at 120 miles per hour. At the exact same time, plane 2 is 225 miles from the airport, and is traveling at negative 150 miles per hour. So what do we want? We want the rate of change of the distance between. So when you read the problem, take a look. What are they actually looking for? Looking for the rate of change of the distance between the two airplanes. That, of course, is this right here, which is decreasing. So that gives you kind of a red light to say, hey, when I get this final answer, it should be a negative value because that area is clearly, as they approach, decreasing. That rate of change, that distance is decreasing, so the rate of change is negative. All right. The other thing you want to think about, this is very different now from that ladder problem in the intro video. It's similar in that, yes, it's clearly we're going to use a right triangle, so it's going to be Pythagorean theorem that we're going to need to use. But there was a constant involved in the intro video. The ladder, as it slid down the wall, if you recall, never changed its length. So because that's a constant, you want to identify if there's any constants right away. You can see where this problem has no constants. All three sides are shrinking as time goes on. So when we set up our equation, which we know is going to be the relationship x squared plus y squared equals z squared, because remember, you need to think about what is the relationship amongst all these variables. And this one is a right triangle. And that comes up in a lot of the problems, this right triangle. And then you ask yourself, well, is anything constant that I can put in right away before I do any differentiation? You don't want to differentiate a constant. Well, if you do differentiate a constant, which you got to know it's 0, but it's easier just to put its value in from the beginning. Unfortunately, there are no constants, so there's nothing we can kind of get rid of right now. We have to keep x squared, y squared, and z squared. So let's go ahead and differentiate and see what we have. And one second, I forgot to write what we want in this problem. We want that yellow highlighted line, which is the rate of change. So it's dz dt. That is what our ultimate answer is, which means after we differentiate, we will not be able to plug anything in for dz dt because that's what we're looking for. All right, let's differentiate. Start with your power rule. So x squared, of course, is 2x, but we are differentiating. Remember, in implicit differentiation, you're used to differentiating with respect to x, so you wouldn't add anything after you did 2x. You wouldn't multiply it because it would be dx over dx, and that just comes to 1. But we are differentiating with respect to t, so you have to put 2x times dx dt. Same as y. Use your power rule. It's 2y. Oh, but that's going to be times dy dt. Every single one of these related rate problems has a dt in the denominator. Remember that. And then 2z dz dt. Okay? So let's plug in what we know, and there's a lot that we do know. So bring down your 2. Our first x, of course, is the 180 miles. Our dx dt is the negative 120 miles per hour. Plus 2. Our y is 225 miles. Our dy dt we have is negative 150 miles per hour. Equals, gotta shrink that a little bit, give myself some space, there we go. 2, we'll come back to z for a minute, just leave an empty space there. We don't know dz dt, but that's okay because that's what we're looking for, so we're just going to write dz dt. Okay, you can't have two unknowns in a problem, right? So when you get to this point, you say, all right, is there a way I can figure out what z is? Because I can't have another unknown variable in my problem. dz dt is my unknown that I want. Remember, at this particular moment in time, y is 225, z is 180. So at that particular moment, you can calculate z itself using Pythagorean theorem. So you can simply get z by doing 225 squared. And you can plug that into the calculator, make sure you got it, and we'll just round it to a nice whole number. Just make it, it's approximately 288 miles, okay? So that means that you can take that and plug it in there. All right? So if you can't get, there's always some relationship to get that unknown so that you're only left with one unknown, in this case dz dt. All right, now you just got to do the math. Okay? You just need to do the math. And also, as you're doing the math, please be careful. So there's all different ways you can do this. You can go ahead and simplify this entire side if you wish, and then divide by 2 over 288. That's fine. I'm just going to go ahead and leave it as it is and solve for dz dt. Again, you do it the way you want, and just as long as you're getting the same answer, we're all good. So I'm going to take my O2 times 180, and I'm going to leave the measurements in there, of course. Okay, I said that and I forgot to put the M here, so let me get that in there. So 225M, I'm just recopying it. And then ultimately I would have to divide by 2 times 288M. All right. So the math itself I'll let you work on, but I do want to talk for a second about the measurements. Okay? So let's do this. dz dt equals, or let's say approximately equals, because there's going to be some rounding in there. So if you take the 2, 180, negative 120, to work that entire thing out, you should get negative 192. All right, but for the measurements for a second, let's look at them in red for a second. Let's see what we have. We have miles, right, times miles per hour plus miles over miles. So what's that's going to give me m squared over hr plus, that's just an m squared over hr divided by another m, which is and m squared divided by hr divided by m times 1 over m. They're going to cancel, and you're left with m over hr. Again, the reason I did that is just to remind you, you know, in science class you've always had to work out your all your measurements to make sure they come out right? An m squared over hr and another m squared over hr, miles squared over hr divided by miles is going to leave you with just miles per hour, because the square is going to go away, which makes sense because that is just a rate of change, a distance, and that makes perfect sense. So even though you got m miles times miles and you end up with miles squared, that miles squared goes away when you divide by the miles. So we're good. And that is a reasonable distance that it is decreasing. We got negative, which is what we expected to get for that particular problem. All right. Now let's do the last one. This one's a little bit trickier. So again, take a moment to read it and set it up. So this is the coffee problem. So we have we call a conical filter. A lot of coffee filters used to look like this. I don't know if they still do. And we have a bunch of information. We also know that our coffee is dripping out of our cone. And it is dripping out at a rate of 2.258 inches cubed a minute, I believe. Let me pause for a second and check that. Yeah. So it's at a rate of 2.25 inches cubed per minute. Couple things. It is decreasing. Well, first of all, think about what kind of measurement this is. Anything squared is normally an area, and anything cubed is a volume. So we're talking about the volume of the liquid. That inches cubed is a key to tell you, oh, I'm working with volume here. Also, the amount of liquid, that volume of liquid is decreasing, so we're going to make this negative. And then let's define it. Well, because it's a volume and it's a rate of change, this is your dV dt. All right? So dV dt is negative 2.25 inches cubed per minute. So we've identified what that 2.25 is. All right? We were also given other information. We were told that the top of the cone has a radius equal to 2 inches. And the full height of the cone is, a little far. Five inches. And we want, let's talk about what we want for this problem. So we want the rate, how deep the coffee level is dropping. When H equals 3 inches. Hold on, got a little squiggly and out of space. How deep is the coffee level is dropping when H equals 3? So depth of that coffee and H are the same thing. So we want the rate of change, the coffee level is dropping, not the volume is decreasing. We're already given that. We want the rate of change, the coffee level is dropping, so we want dH dt. When H is at exactly 3 inches. Okay. So when you look at this particular problem, again, we have a lot of variables here. We don't have any information about we don't know what the radius is at that particular moment. There's a lot we don't know. We have a lot of variables. Are there any constants? So think about, no, the height's constantly changing. We know that because that's what we want to find. Because it is a cone and it's not a cylinder. So think about a cylinder. And a cylinder, like a can or something, the radius remains constant as a water level would drop, right? But in a cone, the radius is also changing. So when we go to set up our formula, which would be a volume of a cone formula, so if you recall, cones and cylinders have very similar volume formulas. The only difference is the cone actually ends up being a third of a cylinder. So it's 1/3. And a cylinder is simply the base, which is a circle, area of a circle, which is pi r squared, times the height. So that is the volume we're working with. It's the volume of a cone. Volume equals 1/3 pi r squared h. Unfortunately, if we go to work this out, we have an r, we would end up with a dr dt, an h, and a dH dt. But we don't have enough, we don't have a dr dt, and we don't know the radius when it's right here. So you've got to be creative and think about, kind of like in this last problem, we had too many variables, but we were easily able to find that z by using basic Pythagorean theorem. This one's a little bit different. We have to use something that you learned back in your high school geometry class. So what I've done here is I am drawing what I call similar triangles. It's kind of like if I took a cross section of this. All right. Oh, I drew it backwards though. Hold on. Let me make this a little bit easier for you. There it is, like this. So up here, my radius is 2. My height equals 5. But at this point, I also have a radius and a height. In fact, you could make what we call similar triangles. You got the little triangle and the larger triangle. So that gives us a relationship between R and H that we can use. And we can say that, oh, R over H, using the idea of similar triangles, is always going to be in proportion with each other. In other words, when R is always going to be in proportion of 2/5. No matter where that level is, R and H will always have a ratio value of 2/5. It gives us a relationship between R and H and lets us multiply both sides by H, say that the radius is 2/5 the height. Since the radius is 2/5 the height, I can eliminate the variable R by replacing it with 2/5 H. And you do all this before you do any differentiating, because we want to get as simple as an equation as possible before we find derivatives. So volume equals 1/3. In place of R, I'm going to put 2/5 H. And then I have an H on the outside. So see what I did as I took away my R and I put in my 2/5 H. Before you differentiate, I want you to simplify this to the best that you can. So volume, so it'd be 4/25 H squared times H. So that I'm going to put 1/3 times pi times 4/25 is going to give me 4 pi over 75 H cubed. That is this equation simplified. Again, do this before you differentiate. You want it in its most simplest form. Now that we only have V's and H's, we can go ahead and differentiate. Derivative of V, of course, is just 1 using our power rule, but we're differentiating with respect to t, so it's actually dV dt. You would bring the 3 out front because 4 pi over 75, again, is a coefficient of H cubed. So it's 3 times your 4 pi over 75 H squared using the power rule. But again, because it's with respect to time, times dH dt. So we have a lot going on there. But we only have 3 variables now. And one of them is the variable we want in the problem. So that's just going to remain an unknown, dH dt. Here's the thing though. We know what H is because we're doing this when H equals 3, and we know what dV dt is. It's negative 2.25 inches cubed per minute. So let's go ahead and fill that information in. And you can start to simplify this a little bit. It's up to you. I would keep it as 4 pi and divide 3 into 75 and give me 25 on the bottom, however you want to do that. So that's 3 inches squared. And this remains unknown because that's what we're looking for. And you can be like, Now I have an equation where I just have one unknown, and I can go ahead and solve for that. Let's clean it up a little bit. Save a little space. I'm going to go ahead, well, I'll do it underneath. You don't have to quite show as many steps as I am, but I want to make sure we're all on the same page. Okay. I need to solve for dHdt. So I need to flip that over, which is going to give me negative 2.25 inches cubed a minute over 36 pi over 25 inches squared. You can work that out however you would like to work that out. You can turn it into, you can flip and do the reciprocal. You can see right away the inches cubed and the inches squares will cancel, and you're just left with inches per minute as our measurement, which is perfect for dHdt. So you're going to be given negative 2.25. If I multiply or divide by 36 pi over 25, multiply by the reciprocal of 25 over 36 pi, I'm left with inches per minute. That, if you plug it into your calculator, comes out to approximately negative 0.497 inches per minute. And that is exactly what dHdt is. Okay. So anyway, there's 3 more examples. This, along with your intro video, should help you be able to work out the problems on the lab. And if you do all the problems on the lab, go over these 3 problems, go over the problems in the intro video, and do the problems in the homework, you'll be prepared for the 1 or 2 that will be on the test.